Good afternoon, and welcome back to the Dudley Smith Farm Winter Meeting. My name is Ashley Bell, and I am an environmental and energy stewardship educator for the University of Illinois Extension. So as a reminder, this meeting is being recorded, and we ask that meeting participants please leave your mics muted and your videos off. And please use the chat box to ask questions, and I will compile them for the presenters to answer at the end of their presentations. So our first presenter this afternoon is Laura Christensen, and Laura is a University of Illinois Crop Sciences Assistant Professor and Faculty Extension Specialist.
Hi there, Ashley, can you hear me?
Yes, I can.
Okay. I will share my screen. Okay. What are you saying right now?
Your presentation.
Okay, very good. Okay. Thank you all for coming back this afternoon for the afternoon portion of the Dudley Smith Field Day. As Ashley said, my name is Dr. Laura Christensen. I'm an assistant professor in the Department of Crop Sciences at the University of Illinois, and it's my pleasure to present to you today about 30 minutes on the first 4 years of our tile drainage research at the Dudley Smith Farm, and we'll wrap up my presentation talking about what we're excited to launch into for these next 3 years coming up at the Dudley Smith Farm. For those of you who have been to the Dudley Smith Field Days before, you will have heard us talk many times about the tiling that was installed on the farm in fall of 2016 with funding from the College of ACE's Office of Research and of course the Dudley Smith Initiative funding. The original project that we had is listed there at the bottom of the screen. We'll talk mostly about that, and we'll also talk about some additional investments that have been made into the farm and into our research in the coming minutes. As a recap on what exactly we have going on at the tile drainage research portion of the farm, we have 16 plots, essentially 16 plots. Fast fact though, there's actually 17 individually drained plots at the Dudley Smith Farm. Each of these plots are 2 acres in size. The blue lines that you see on the screen are each a tile drainage lateral. So that's a 4-inch diameter perforated tile pipe. The tiles are generally spaced 60 feet apart, which means that each of our plots, the majority of the plots are 180 feet wide by 500 feet long. And so the important thing for our research and monitoring the tile drainage water is that each of the plots drains to a control structure, this little gray box, which is illustrated with that little black square that you see on the tile map behind the picture. Now that little gray box is called a control structure, and it's essentially like a manhole or an access port down to the tile pipe. And so through that access port, we can stick our sampling tube from our automated water sampler, or auto sampler, which I'm showing here, this little gray machine looking thing. That auto sampler, inside it has water bottles, so just water sample collection bottles, and the top of the auto sampler has a small computer and a small pump. This allows us to collect a water sample from each of those drainage plots whenever we program the computer to kick that pump on. So that's how we collect our water samples at the Dudley Smith Farm. Another feature of each of the 16 plots, individually drained plots at the farm, is that each plot had a gas sampling chamber. Now, in terms of nitrogen in our fields, we can lose nitrogen through our tile drains in terms of nitrate that leaches down to the tiles, but you can also lose nitrogen from our fields when nitrogen gas, primarily nitrous oxide, which is a greenhouse gas, when that nitrous oxide filters up out of the soil. And so this is what the gas chambers were designed to allow us to measure how much nitrous oxide was leaving the field, filtering out through the surface of the soil as gas. I'm not going to talk about our gas results today, but that was an important part of the first 4 years of research that we were doing. You'll also notice that we had at the northern end of the site or at the farm a bioreactor, which I'm showing the outline of here. We'll talk a little bit about the results from the bioreactor. Really, the northern plots or the north half of the plots drained to that wood chip bioreactor. And I'd be remiss if I didn't talk a little bit about some other infrastructure upgrades that happened on the Dudley Smith farm over these past 4 years. Importantly, we had support from the Office of Research to build our own shed. It's quite a ways from campus, and so having our own little shed out there allowed us to keep some equipment on site rather than trucking things back and forth all the time. So we're thankful for that. We're also thankful that it seems like a small thing, but the Office of Research allowed us to gravel the access road, which was important because that was generally the lowest part of the field. So that was the part that was always wet where we were trying to drive. And so it was really a nice infrastructure upgrade to have a nice gravel road in and out to access our plots. Now, if you're interested in the specifics of exactly how we do what we do or what was happening at the Dudley Smith farm in terms of the tile drainage plots, we're fortunate that one of the first graduate students from this project, Mr. Giovanni Preza Fontes, wrote a nice summary article that describes all of our methods out at the Dudley Smith farm in terms of the tile drainage research out there, and that article is publicly available. So what exactly did we have going on in the field in terms of these 16 drainage research plots that we had, that we have at the Dudley Smith farm? Like I said, there's 16 plots. We wanted to do 4 treatments. That means we replicated each treatment 4 times. So 4 times 4 gives us our total 16 plots. The first treatment that we'll talk about is our control. So it's not really a treatment, it's a control. And the control was not applying any nitrogen fertilizer to corn. So we were growing corn on these 4 plots, but we did not apply any nitrogen fertilizer in any of the 4 years of the study. That might seem kind of ridiculous. If you're a farmer growing corn, you would never not apply nitrogen fertilizer, but this allowed us to answer an important question in terms of, if we take nitrogen fertilizer completely out of the equation and we're still growing corn, how much nitrogen do we lose through our tile drains? And so that's an important question just in itself. Moving now into the actual treatments. Our first treatment we call the pre-season nitrogen application treatment. Now treatments 2, 3, and 4, which we'll talk about, all 3 of those treatments received a total of 200 pounds of nitrogen per acre. A total over the year. But the timing of when those 200 pounds of nitrogen was applied, that's what differed between the treatments. So for example, starting with treatment number 2 here, our pre-season nitrogen application, the intention with this treatment was to apply most of the nitrogen in the fall and the small balance of nitrogen pre-plant. So the first year of the study, we applied 120 pounds of nitrogen per acre in the fall with the balance of 80 pounds of nitrogen in the spring. That was 2018. Now the 2019 and 2020 cropping year, we couldn't get any fall nitrogen on. And that was very reflective of conditions happening locally. I would say a lot of farmers had trouble getting fall nitrogen on these past 2 years, and as we did. So in 2019 and 2020, our second and third year of the study, we applied all of the nitrogen for this specific treatment, 200 pounds per acre applied pre-plant. So that was in one bulk. We compared that treatment number 2 to treatment number 3, which was really our recommended nitrogen application strategy of in-season nitrogen application. So for this treatment number 3, we applied 120 pounds. Let me have my cheat sheet. Nope, we applied 80 pounds of nitrogen pre-plant, 80 pounds per acre pre-plant, and then the balance, 120 pounds of nitrogen, was applied as a side dress. And we were able to do that consistently in all 3 years. So 80 pre-plant plus 120 pounds of nitrogen per acre as side dress. And that was the recommended or the improved nitrogen management treatment. Now, treatment number 4 was exactly the same as treatment number 3 in terms of how we applied nitrogen fertilizer, but for these last 4 plots, we did in-season nitrogen application plus a cereal rye cover crop. That was, of course, planted the previous fall and left to grow over the winter and early spring. Now, what did we find in terms of tile drainage nitrogen loss. Across the bottom of this graph, you see our 4 treatments: 0 in control, pre-season nitrogen application, our in-season nitrogen application, and then in-season plus the cover crop. That was where we were really trying to throw everything at it to keep nitrogen out of tile drainage. The y-axis on this graph was nitrate nitrogen in tile drainage that we were losing in terms of pounds of nitrogen lost per acre. The different color bars are the different color years of the study: 2018, 2019, and 2020 cropping years. Now, the first thing I want to point out is the error bars on these graphs. And so the error bars are really big. That indicates a high level of uncertainty or a high level of variability within the 4 plots that were making up each of the bars here. Remember, I said 4 treatments replicated 4 times. So each bar here represents 4 plots in a given year. Now, these large error bars or large variability for each of our treatments, that's not something that we did wrong as researchers. It's not something that our tile drainage contractor did wrong. There's nothing wrong with the site. This is just really reflective of natural variability of a large scale study like what we were doing. So there's a lot of variability at the site. Another thing I want to highlight is that 2019, as many of you will remember, was a very wet year. Significant flooding in 2019, and indeed that's where we saw some of our highest nitrogen losses from a lot of our treatments. And just to show you what the farm can look like, I found this picture as I was making this presentation, and I thought, oh, that does a pretty good job of illustrating how wet, especially the driving path can be at the Dudley Smith farm. And then I found this picture, which I thought really illustrated some of the challenges that we have dealt with our tile drainage research at the Dudley Smith farm. But this picture also reminds me to be very thankful to our staff and our graduate students, our visiting scholars, our undergrads, who are always responsible for collecting our day-to-day drainage water samples at the farm. We could not do what we do without their hard work in the field in conditions of all kinds. And also, even though we've improved the drainage in this part of the field, if you get a lot of rain in a short period of time, you're just going to have surface ponding and flooding like this, no matter how good your drainage is. And that's important to remember. Okay, so now jumping forward to a summary of the tile drainage in-loss over the 3 years. So rather than looking at individual years here, now we're looking at a summary. On the bottom of the graph, again, you see our 4 treatments, and the y-axis is still the same, nitrate loss in the tiles in terms of pounds of nitrogen loss per acre. The first thing I want to point out in terms of summary findings, there is no statistically significant difference in nitrate loss between the pre-season nitrogen treatment and the in-season nitrogen treatment. Now, in terms of the statistical test that we ran, the way I know that there's no significant difference, there's an A here, and then there's an AB here for the blue versus the dark orange bar. The fact that there's an A on both of those bars means that those treatments were not significantly different. And so even though the bar looks different, the error bars are overlapping sufficiently for us to not have confidence to say that there was a statistically significant difference. So essentially, this means that switching to in-season nitrogen application did not significantly improve water quality compared to the pre-season treatment based on the statistics. However, we did see a significant reduction in nitrate loss through the tiles when we added in that cereal rye cover crop to the in-season nitrogen application. We saw a 32% reduction in nitrate loss through the tiles when we moved nitrogen application in season and added in a cereal rye cover crop. One additional note I want to point out about this graph, coming back to our control treatment. Remember, we applied 0 nitrogen fertilizer. We did not apply any nitrogen fertilizer to these 4 plots over the 3 years. And we still lost nitrogen through the tile drains. And so this is important because the nitrogen we were losing through the tile drains, that was coming from the soil. And when we think about our very valuable, rich, amazing soil in Illinois as a resource, I hate to think that we're losing nitrogen that's naturally inherent to our soil out through our tile drains. And indeed, we see we were losing 10 pounds of nitrogen per acre from the soil out through our tile drains with those zero nitrogen control plots. Of course, I would be remiss if I did not show our corn yields. This is a very important part of balancing agronomic goals and water quality goals. And the good story here is that there was no sort of corn yield penalty by doing some of these recommended in-field water quality practices. So you see A, there was no statistically significant difference in the yields when we looked across the 3 years for those 3 in-field treatments. Of course, if you don't apply any nitrogen to corn, surprise, surprise, you don't get a very good yield, but I think you all already knew that anyway. Okay, so takeaways from the infield portion of these first 3 or 4 years at the Dudley Smith tile drainage research infrastructure. Firstly, nitrogen loss is highly variable. That's why we have replication at our site. That's why we do studies for multiple years. The nitrogen loss was just highly variable, like we talked about with those big error bars when we were looking at individual years. Second takeaway, if you get a lot of rain, you're just going to have a lot of drainage water, and that inherently means you're going to have a lot of nutrient loss when you're growing annual crops like corn or like soybeans, which we didn't grow in this case at the Dudley Smith farm. But, you know, that's kind of a downer of a message because the amount of rain we get and the timing of the rainfall is somewhat out of our control. But that's where some of our recommended practices can come in because the practices are things that we can control, whereas rainfall is not something we can control. So we will need layered practices to make a significant headway towards meeting our water quality goals. Starting at the bottom, I consider the base of the pyramid improved nitrogen management. While we did not see a significant difference between moving pre-season nitrogen application to in-season nitrogen application, those 2 treatments were not different in terms of nitrogen losses through the tile drains. We do know that managing nitrogen fertilizer correctly and as best we can every year, that's still very important. So I consider that a baseline practice for us to be able to meet our water quality goals. But improving nitrogen fertilizer management on its own isn't going to solve our water quality problems. So that's important to realize. That's why it's the base of this pyramid here. Next step on the base is our winter cover crops, which we did see when we added that in for the in-season management, we did see a significant reduction in nitrate loss through our tiles. And then the top of the pyramid is our edge of field practices, which is very convenient. We're going to talk about that next. The edge of field practice that we're studying at the Dudley Smith farm is called a wood chip bioreactor. A wood chip bioreactor is a trench or a pit full of wood chips that we route tile drainage through. Inside the trench, we enhance the natural process of denitrification, which is the conversion of nitrate to nitrogen gas. That's not a process that we want to be happening in our field, in the soil, but in a bioreactor, it is a process we want to happen because that's how the wood chips and the bacteria in the bioreactor clean the nitrate out of the water. And that's what makes this an edge of field practice. Now, the interesting thing about the Dudley Smith farm bioreactor is that it is one of a kind in the entire world, to my knowledge. There's a number of bioreactors around the world, but this is the only one that has 2 flow routing baffles. You see these plastic baffles right here. The point of those baffles is to route the water more efficiently through the wood chips. Usually water would just flow straight through the wood chips, but in this case, we wanted to try something very different with the bioreactor we built at the Dudley Smith farm, so we added baffles. After 3 years of research here, what we found is that this bioreactor was treating about 40% of the flow coming from the plots that were routed into this bioreactor. And in terms of our annual nitrogen loss reduction, we were removing between 22 and 24% of the nitrate that would otherwise have moved downstream. So this was a little bit disappointing, but also not terrible news. Normal bioreactors that, for example, don't have baffles remove between 20 and 25% of the annual nitrogen that would otherwise go downstream. And so while we didn't necessarily improve, we didn't revolutionize how we do bioreactors with this bioreactor here at the Dudley Smith farm, we were operating on par with what we expect bioreactors to do. And so a little disappointing that we didn't revolutionize bioreactor technology, but it was still good news that we were cleaning nitrogen out of water like we expected. One important finding, the reason that we suspect that we weren't revolutionizing bioreactor technology is we realized actually very quickly that the drainage at the Dudley Smith farm is a little unique. It's different from a lot of our other tile drain sites across the state in that the drainage at the Dudley Smith farm is flashy. And what I mean by flashy is that we get rain, the tiles flow full, full force, and then they stop flowing very quickly. And so rain, a lot of drainage, and then drainage stops. Rain, a lot of drainage, and then drainage stops. The drainage is flashy. And that impacts how edge of field practices like wood chip bioreactors work. And so we didn't realize that before. We didn't have any field scale data documenting that sort of flashiness of drainage systems can impact how our edge of field conservation drainage practices can work. And so this was a really important finding for us. And our second student to graduate from the site or to be involved with the site, Ms. Hannah Doherty, her master's thesis about this bioreactor with baffles, this is now published if you're interested to find out more. Okay, so that's a little bit about what's going on with the tile drains at the site, what we've been finding with our research. I also want to highlight, I want to switch gears just a little bit and talk about all of the investment and all of the collaboration that's happened in terms of the tile drainage research these first 4 years. And this is a big table with a lot of information, ways that we've leveraged funding from the College of ACES and funding from the Dudley Smith Initiative. I'm just going to walk through a few of these that serve as good examples. One of our most important partners for this work was Illinois INREC, Illinois Nutrient Research and Education Council. And one of the important things that their funding allowed us to do in very early days was purchase the automated samplers. So I showed you these automated samplers a couple minutes ago when I started the presentation, so you know kind of what the automated water samplers look like. But I just want to illustrate why they're so important. If we didn't have the auto samplers and we were driving down to the Dudley Smith farm from campus, say once a week, and collecting water samples by hand, if we were doing this, for example, at plot number 8, remember we have 16 plots, but just say plot number 8, this is what our data would look like in terms of as time goes by on the x-axis, and this is on the y-axis nitrate concentrations. So if we were collecting samples by hand, driving down once a week, this is what our data would have looked like. Of course, we have auto samplers, and so we can program those auto samplers to collect water samples basically whenever we want them to. And so our data look more like this. It's much higher resolution information in terms of nitrate leaving the field and the tile drains. And I'll highlight especially this point right here. If we hadn't had the auto samplers, we would miss some of our highest sampling points for nitrate. And so this is really important resolution for our data. Another project I want to highlight was an important leveraging of the tile drainage investment made at the Dudley Smith farm is this FFAR, Foundation for Food and Agriculture Collaboration. This made the Dudley Smith farm, DSF, Dudley Smith farm, part of a multi-state drainage network. I'm showing that multi-state network here. You see the Dudley Smith farm. We're actually one of the farthest south site for this drainage network. But the important thing about this network, all 8 of these sites, all 8 of these research sites have replicated drainage plots, just like I showed you at the Dudley Smith farm. And so you see the 8 sites listed there. And it's actually an international network because we have one site in Ontario. So we like to promote ourselves as, international high flyers. This is a clip of the data entry portal that we have for this multi-state international project. And the important thing is that we're all collecting biomass samples, soil samples, water samples, and gas samples for some of the sites. We're all collecting those in a consistent way. And so if you think about the 8 plots that we have at the Dudley Smith farm, rather than just, or 16, if you think about the 16 plots that we have at the Dudley Smith farm, rather than just 16 data points in a given year, we actually have over 100 data points in a given year by being a part of this drainage research network. So it's very powerful, and it's a great group of people to work with. Now, the last project I want to highlight off of here, the last leveraging that we've been able to do with the Dudley Smith farm over these past 4 years, is this collaboration partnership with the Christian County Farm Bureau. And in terms of monetary value, this is the smallest collaboration that you'll see on this list that I've compiled here. Smallest monetary value, but I think one of the most important ones in terms of importance, and especially in terms of connection to the local community. And I'll say that I'd never had the pleasure of meeting Mr. Dudley Smith Jr., but I do think that he wanted us as researchers to be connected to the local community. And he wanted to make sure that the work being performed at the farm had strong local relevance. And so this is one project that I'm especially proud of. This allowed us to trial our heated auto sampler enclosure. So let me talk about that for just a second. I've talked about the auto samplers a couple times. So you see those here. The important thing about auto samplers is that while they're intended to be deployed in the field, that's the point, and so they are somewhat field hardy, you really can't leave them out in really cold conditions, or you'll start to have problems with, for example, the water freezing. And so with this trial grant, or this small grant with the Christian County Farm Bureau, we were able to purchase the setup of these custom-made insulated enclosures. So you see the insulation here, trialed with a propane-powered water heater to keep the enclosure warm enough so that we could keep that auto sampler running all winter. So we didn't have to bring all of the auto samplers back to campus. And of course, we do have drainage happening during the winter at the Dudley Smith farm. We did just a couple weeks ago. And so it's important for us to be able to keep our auto samplers out there all winter. In fact, we trialed these heated enclosures with that funding from the Christian County Farm Bureau and the Illinois Farm Bureau. And of course, we have since then rolled out this sort of setup for all 16 of our plots. Okay, so now launching forward, that's the first 4 years at the Dudley Smith Farm tile drainage research plots. Now I want to talk about looking forward to the next 3 years. And we're fortunate to have received funding from the ACES, College of ACES Office of Research through the Dudley Smith Initiative to continue our work, because this is a long-term investment, and we want to make sure that we're doing right by that long-term investment. So don't feel like you have to read these 4 objectives. We'll go through them very briefly, one by one, starting with the first one. Determine the effects of combining water quality practices on corn production and tile drainage nitrogen loss. That should sound very familiar, because that's just a continuation of what we've been doing these first 4 years. And just as a reminder, the reason why this is so important for us to continue is this variability that I talked about before. And so moving forward, this cropping year, we're actually continuing these same exact 4 treatments that you see listed down here at the bottom. After the end of this cropping year, we're going to look at how we can start to change up some of the treatments, but we're going to continue to evaluate water quality conservation practices on crop yield and water quality. A new thing that we're going to do in these coming 3 years at the Dudley Smith Farm tile drainage plots is evaluate opportunities around real-time tile drainage nitrate sensors. This is really exciting. These sensors are not cheap, as you can see from the screen, and they have never, to our knowledge, been trialed or tried with tile drainage. Probably because they're so expensive. But we're going to try these different sensors that allow us to sense nitrate concentrations in drainage with very high frequency and load that information onto the internet. So this is really cool, because you could be sitting at your house, or I could be sitting on campus and check in on a website and see what the nitrate concentrations are in the Dudley Smith drainage water. That's really exciting for us as researchers, and I hope you find that exciting too. So just to illustrate the benefit in what these sensors could provide, I showed you this before. This is an example of what the data would look like, what the nitrate concentrations are, our understanding of what the nitrate concentrations would look like if we were driving down every week, collecting a water sample from, for example, plot 8 by hand, and then analyzing that sample in our lab. Like we discussed, we of course have automated samplers at the Dudley Smith farm. So our data actually look like these orange dots in terms of nitrate concentrations. But with the real-time nitrate sensors, we won't have these gaps between points, which is really amazingly high frequency data. This is at the cutting edge of water science to be able to have high frequency data like this. We're very excited. I'm very thankful to the Office of Research and the Dudley Smith Initiative for letting us try something so new. Now, objective 3, again, launching forward, we're going to continue to communicate results to the agricultural community, hopefully through field events, maybe sometime soon, hopefully in person again. I think we're all missing that. But I think the Dudley Smith Farm and the Dudley Smith Initiative have always been a great trialing ground or proving ground to try new things. And so, for example, our real-time nitrate sensors, where you can access that information on the internet in real time, that's another way that we're going to be working to engage the public with our research at the Dudley Smith Farm. So that's a way we're going to continue to move our outreach programming forward at the Dudley Smith Farm through those, with using those nitrate sensors, in addition to the normal things we do like field days. And then our last objective, looking forward to the next 3 years at the Dudley Smith Farm, it felt like it was time to make this an explicit objective of what we're going to do, promote the Dudley Smith Farm as world-class research infrastructure. Why? Because it is. And it's time for us to really celebrate what we have at the Dudley Smith Farm. There's millions of dollars of investment just on the tile drainage research itself that we're so proud of. And so we're going to look to increase collaborative use and increase leverage funding going into this farm. So with that, I'm at the end, nearing the end of my time with hopefully a little time for questions. But I do want you to leave today, if you leave with one concept or leave with one idea from this field day, I want you to understand that it's more than just research at the Dudley Smith Farm, especially for us with our tile drainage research there. It's really about the people. And I think this is something hopefully that would have resonated with Mr. Dudley Smith Jr. The number of lives that have been touched with our tile drainage research over these past 4 years has been really significant. And so I thank you for that. And with that, thank you. I think we have some time for questions. And then we have a graduate student, one of my graduate students, Miss Ariana Munoz, coming up next. And Ashley, I can introduce her whenever we're done with the questions.
Okay, so Laura, what are your thoughts on applying pre-season nitrogen along with the cover crop of cereal rye?
Good question. Such a fair question. We did not have enough plot, though this is the researcher answer, we did not have enough plots to do pre-season nitrogen combined with the cover crop. And so based on our data, I technically can't say what that benefit would have been because we simply didn't have enough plots to actually do that. I do think that I'll reiterate, managing nitrogen as best we can in every year, and hopefully that means more in-season nitrogen applications. I do think that's important to be trying to do that every year. But I also understand that it's just often difficult to do in-season nitrogen applications. And there's a lot of risk involved for farmers to do that. And so that nitrogen management is the base of the pyramid, always striving to manage nitrogen fertilizer as best we can. That generally means more in-season if possible. But if that's not possible, really trying to get that cover crop thrown into your mix, I think that's the next best step. And I think the cover crop is going to provide more water quality benefit than just changing the timing on the nitrogen fertilizer. But that doesn't mean nitrogen fertilizer timing isn't important. It's always important to manage nitrogen fertilizer as best we can. But we do love cover crops too. I hope that was an okay answer. Ashley, is there another question?
Yes, so for the in-season nitrogen with cover crops, when was the cover crop terminated compared to planting dates?
Oh, I don't have my cheat sheet on that. So I will say that varied every year. The cover crop was always, so I'm wondering if Kristen Greer is online. Kristen, if you have any thoughts about this, I don't want to put you on the spot. She's our main agronomist for our research site. I do know the cover crop was terminated prior to planting dates. I don't know if it was like 2 weeks before or 3 weeks before. And I know that
Can I
varies.
make a comment?
Yes, thank you, Kristen, for weighing in.
So yes, our goal was always 2 weeks before planting, but with rainfall events after cover crop termination, that has stretched out to 3 weeks or even a month. I think last year it was 1 month prior, or 1 month planting after termination.
Thank you, Kristen. Well said, and well interrupted. That was perfect. And I'll say that that's one thing that's been important for us as researchers and extension specialists to realize how difficult it is to get the timing of cover crops right. We promote cover crops all the time for water quality, but to kind of feel like we're living through this process of making decisions about termination for cover crop and planting cover crop, it's made it very real for me personally as a researcher to understand everything that's involved in making decisions about cover crops. It's not simple, for sure. It's just like managing any other crop. Okay, Ashley, I think there might be one more question.
Yes, what is considered a lot of drainage?
That was the summary bullet, so that's relative. So in 2019, in 2019, there was a lot of rain, particularly in the spring. There's a lot of delayed planting. And so we, in particular, just had a lot of flooding at our plots. And so that presents challenges in terms of managing or monitoring all of the water. In general, a rule of thumb in general is you'll have a roughly 25%, plus or minus 5%, 25% of the total annual precipitation will leave the field through the drains. So if you get 36 inches of rain on a long-term average every year in a tile drain field, you'll generally lose 25% of that would be 9 inches of drainage. And so in wetter years, that tends to go up. You could have 50% of your precip leave the field as drainage, and so or higher, which indeed we saw with some of our plots. Yeah, I don't know if that answered the question.
Okay, we have one final question here. So are we seeing farmers in Illinois installing bioreactors? And if so, what has been their experiences?
Well, I'd like to say their experiences have been great because I'd like to see a lot more bioreactors go in. We have seen an increase in bioreactors over the past 2, 4, 10 years. I think based on our 2017 biennial report for our nutrient loss reduction strategy, I think we had 17 bioreactors in the state, or 19. Our 2019 biennial report for our nutrient loss reduction strategy, I think we had 36 bioreactors. And so based on those numbers, I might be off 1 or 2 in the count just because I'm quoting from my head. But based on those numbers, we are seeing an increase in the number of bioreactors in Illinois, also in Iowa, also in other states across the Midwest that have a lot of tile drainage. I think farmers that are putting bioreactors in tend to be at the forefront of conservation, often at the forefront of some of the farm organizations within their local communities. And I think they're really tend to be farmers who are doing a lot of things in the field already. They're following 4R's nitrogen management stewardship approach. They're doing cover crops, and they're just looking for that next thing to make sure that they are being good upstream neighbors. So that's a consistent theme across the farmers that I've been working with who have bioreactors. They're really engaged in what's that next thing that I need to be doing to make sure I'm a good upstream neighbor. Yeah, and I think they appreciate that the bioreactor doesn't require a whole lot of management. Like cover crops, I talked about, there's a lot of management decisions involved in that, as there are with managing nitrogen fertilizer. So I think there's a lot of benefit for a bioreactor that's just there at the edge of field cleaning water on its own without a lot of hassle.
Thank you so much. Would you like to introduce our Ariana now?
I would, yeah. Ariana, if you want to start to share your screen, I'll do a quick introduction. Miss Ariana Munoz joined our research lab here at the University of Illinois in the Department of Crop Sciences about 2 years ago. She's been one of our standout students. We're so fortunate to have her. She's going to talk about her cover crop research today and end up describing how that relates to work that she's done at the Dudley Smith Farm. To set the context for Ariana's work, I want to start by just reiterating that we love cover crops. We love cover crops, and we want everyone to do cover crops as much as we can. But that's where Ariana's research comes in, because we also realized through this experiment that there is no perfect practice. And there are sometimes trade-offs, even with a practice as amazing as cover crops. So Ariana, go ahead and take it away.
Could I interrupt for a moment, Laura?
Yep, go ahead.
This is Len Corzine. I'm going to have to leave soon, but I wanted a quick question. I lost my connection for a bit. Good presentation. I do have a question on your slide that showed the summary analysis of nutrient loss, of nitrogen loss, that showed no significant difference between preseason and in-season. Right. And then you compared your in-season to in-season, or compared to the N plus cover crop. You kind of manipulate, or it looks like your analysis I didn't quite agree with, because there is, I guess depends on how you read it, almost as much difference from preseason to the regular in-season as there is from in-season to the in-season N plus cover crop. And then you went back, and to show the reduction, you went back to the higher one to use. You know what I mean? Could you explain that a little?
Yeah, and I know I feel like we've talked about this before, and it's a very valid point, but I will say that part of the challenge is that the variability for the individual treatments impacts if you see a significant difference between certain treatments. And so, for example, the preseason nitrogen application, those plots tended to have a lot of variability in terms of nitrogen loss. And so, like, for example, the error bars were really big on that one, meaning that it was overlapped. I think statistically you could consider it as being kind of overlapped with the infield nitrogen management, nitrogen loss. And so that's why we can't say that there's a significant difference that between the preseason and the in-season. And that's very consistent, Lynn, I'll say, with other studies across the Midwest. There's often, in studies that are comparing nitrogen management, especially different timings, there's often no significant difference when you look at like a preseason versus an in-season in terms of nitrogen loss. So what we found was very consistent with a number of studies from Iowa, from Minnesota, from other states that have been done over the past 10, 15 years. And so that's why I'm confident, I have a lot of confidence in our research and have a lot of confidence in how that gets presented, because it's consistent with other research. Nitrogen management is important, but it on its own will not allow us to achieve our water quality goals. We have to have other practices beyond simply changing the timing. Lynn, I think this is something that we'll probably continue to discuss into the future as we continue at the Dudley Smith Farm. And I thank you for your questions. They keep us honest for sure. Ariana, thanks for allowing that little side note. Do you want to take it away now?
Yes. Can everyone hear me?
Yep, you're good.
Okay. So thank you for the introduction, and I'm excited to be here and to talk to you about a project that we carried out here in Crop Sciences greenhouses in our rainfall simulator. So the title is Nutrient Leaching from Packed Soil Columns with Cover Crops Exposed to Freeze-Thaw Events. So to start off with, as you may know, subsurface tile drainage has been used in the US Midwest for more than 150 years. And although this has increased our production, it has also increased the amount of nutrients that are transported to water bodies. But we have implemented new conservation practices and new technologies to be able to reduce these nutrients. And one of the ones that we're most interested in is our cover crops. As you may know, all of the added benefits that they have, such as reduction of soil erosion, they also help retain nutrients from our fields. So there have been a lot of studies that talk about how vegetation may aggravate dissolved nutrient losses, especially when they're exposed to freeze-thaw events. So it would depend on the amount of nutrients that the plant has, the amount of biomass that there is, as well as the amount of moisture that the plant has. It will be the amount of nutrients that can be leached. And a bunch of these experiments have been done in laboratory settings where they have used clipped vegetation samples and have evaluated leaching from these plants. So we wanted to do a study that combined having the plants growing inside of the soil and to be able to collect runoff and drainage samples without having to clip our vegetation. So before I start, I want to talk about how the processes that happen when plants and soils are exposed to freeze conditions. So first, we have the factors that are below the figures and our processes above the arrows. So first we have the plant and the soil. They can vary in characteristics in the plant development stage and how much water the plant has. So when these two are exposed to freeze-thaw conditions that can vary in temperature, duration, speed, and number of cycles, there's a bunch of processes that can happen. The one that we're interested is in plant cell lysis. So what this is, it is when plants are exposed to freezing events and then ice crystals form inside of the tissue. And then this will lead for the plant to start to decay and to release the nutrients. So this nutrient loss can be exacerbated by snow melts or by rainfall that can vary in volume and intensity and in time. And then this can mobilize and transport the nutrients as dissolved and particle bound into our water. So all of these processes are complex and we don't have them all figured out. So reason why we wanted to do this work to have a better picture of what is happening. So our hypothesis was that different levels of freezing will affect the nutrient concentration of runoff and drainage samples from the two cover crops used. And our objectives were to determine the effect of freeze-thaw events on nutrients leached from cover crops and packed soil columns, and to determine if there's a difference in nutrient concentrations in runoff and drainage water samples depending on the freezing temperatures. So first, I'm going to give you a little overview of how the project was done. So we set up an experiment with PVC columns. They were 8-inch PVC columns, and we filled them up with soil and we planted cereal rye or radish. And we also had bare soil treatments that acted as their controls. We exposed them to freezing events, which varied in a heavy freeze and a light freeze. And also we had a no freeze as a control. And we also had the rainfall events that varied in a high intensity and a low intensity. So then after all of this, we collected the runoff and drainage samples to be able to take them to the lab and analyze them for total phosphorus, dissolved phosphorus, nitrate, and total suspended solids. So for you to get a better picture of how the columns looked, here are a picture of the columns in the greenhouse. They were inside the greenhouse for about a month to be able to let them grow and have a good amount of biomass before the freezing events. We chose cereal rye and radish because They're one of the most popular crops used, especially cereal rye. And also we wanted them to be a little bit different in the sense that cereal rye is a winter hardy cover crop, while the radish tends to be less tolerant to freeze. And they also have different roots. And here are the ports that we installed to be able to collect our water samples. So these are the runoff ones, and these are the drainage. So here I have first pictures of the heavy freeze event. This was done for 8 nights from temperatures ranging from -12 to 12 degrees Celsius. What we did was that we just took the cover crops outside of the greenhouse and let them be with the temperature that was already outside. And this first pictures are on night 2. These are around night 5. And this is around the last day that they were outside. So we can clearly see how the tissue was damaged, especially in this radish, where it almost disintegrated. And then we have the light freeze. This was done for 2 nights for temperatures ranging to -1 to 12 degrees Celsius. So it wasn't a very harsh freezing. And you could see that there's little to no tissue damage after they were exposed to the freezings. And then after we froze them, we took them to the rainfall simulator. A lot of my lab mates had to help, and you can see they were not pretty happy. They were very heavy columns. Each one of them weighed about 100 pounds. So thankfully, we ended up taking them to the rainfall simulator. This is the picture that you see here on the right. And we were able to perform our rainfalls. So we had the high intensity was 6.9 centimeters per hour and a low intensity of 4.6 centimeters per hour. And these were done for a total of 2 hours. And we collected the runoff samples after 30 minutes that the runoff started. So we would time that when the column started to run off. So it was unique for each column. And we also collect the drain samples 24 hours after the rainfall simulations. So after doing the analysis, we found some interesting stuff. First, I'm going to talk about the runoff. Here I have total suspended solids, the total phosphorus, and the dissolved phosphorus under the heavy freeze, the light freeze, and the no freeze. So first of all, we can see that the presence of cover crops notably reduced the total suspended solids in the light freeze and the no freeze treatments. And you can see the big difference here with the bare soil that had total suspended solids of almost 1,000 milligrams of suspended solids per liter. And then when we look at the total phosphorus and the dissolved phosphorus, especially under the heavy freeze conditions, we can see how the cover crops exposed to the heavy freeze conditions presented higher phosphorus concentrations. Something to note here is that the cover crops for the total phosphorus, they had concentrations up to 1 milligram of total phosphorus per liter. And this is above the concentration limit that has been established by the US EPA for the Midwest, where lakes can have 0.038 milligrams of phosphorus per liter and streams 0.076. So they were above what we needed, and we can see how this can relate to the freezing conditions and how the tissue was damaged. So there was probably a lot of leachate that left the cover crops. And then in terms of the drainage, here I have total phosphorus, dissolved phosphorus, and nitrate. I'm not showing total suspended solids because there was no difference. But first, I want to talk about the total phosphorus. Here, the cover crops exposed to the heavy freeze had higher total phosphorus concentrations than the bare soils. And in the dissolved phosphorus, we didn't see a big difference, but we can still see that there was a little bit more of dissolved phosphorus leached by the cover crops. And also in terms of nitrate, we saw that the presence of cover crops consistently and significantly reduced the nitrate concentrations regardless of the freezing conditions. As you may see, the bare soils had way higher concentrations than the cover crops, and it didn't matter what type of freezing conditions it had. So for our conclusions, we have that the severity of the heavy freezing conditions created notable differences between the treatments for many of the analytes, especially for the total phosphorus and the nitrate in both the runoff and the drainage water samples. And we also found that the presence of cover crop significantly reduced nitrate concentrations in drainage water across all freezing events. And like this could also be related to what we have found in the field, that cover crops help reduce the nitrate concentrations. And although there are significant trade-offs in the two cover crops versus the bare soil, these can be inconsequential in field conditions because there are other potential sources of phosphorus and nitrate, and there are also more added benefits to how the cover crops can help in the field. So after finishing this lab study, we did a intensive tile drainage study at the Dudley Smith farm to be able to see how this would be in the field. So as Dr. Laura Christensen mentioned, this is our treatments at the Dudley Smith farm. The ones that we were interested in are the no cover crop and the cover crop ones. These are the in-season and the in-season plus cover crop. So what we did was that we did an intensive study for 4 weeks where we sampled every 6 hours because we wanted to see if when the temperatures fluctuated throughout the day, if there was going to be a higher amount of phosphorus in our tile drainage after they were frozen, and then if the temperature would rise, they would start to thaw and release those nutrients. The cover crop planted here was cereal rye. It was air seeded in late September of 2019, and there was no fall nitrogen applied during this year. And we collected our water samples with these automated samplers that were also shown by Dr. Christensen. And we had to go to the field every 3 days. So it was a lot of work, but thankfully we had the help from our interns and from our undergrad students that made the job a little bit quicker. And here I have some pictures of the field. This is the driveway that after a flooding event, it got frozen. So we had temperatures ranging from 18 to negative 18 Celsius. So that's about around the 60s to 0 degrees Fahrenheit. So there were a lot of differences in temperatures. And here are also some pictures of the cereal rye. This is cereal rye growth, and we collected biomass samples to be able to analyze them for nutrients. And right now, we're still we're doing preliminary data analysis, but so far we're not seeing differences between the plots that don't have a cover crop and the ones that do have cover crops. And but something that could be that we could talk about is how we could probably use more of cover crops that are more winter hardy, that won't have a lot of tissue damage after freezing events, and also keep in mind all of the benefits that they have. And here's just a funny picture of me learning to drive the gator when we were out in the field. So yeah, if you have any questions, I'm glad to answer. Thank you.
Thank you. Are there any questions? Feel free to post them in the chat box. All right, thank you so much. So, Laura, if you're still available, there was a question about the lifespan of bioreactors. Could you address that while we get the next presenter set up?
Yeah, that sounds good. Great job, Ariana. I think before I answer the question, I'll just reiterate that Ariana's study is so fantastic because she was able to do a small scale controlled experiment on campus where we definitely observed this physical leaching of phosphorus from plant tissue, cover crop tissue, when it was frozen. And she confirmed that with a very well designed, very good experimental design study, a small scale study on campus. But then when we went up to the field scale and tried to evaluate if a similar thing was happening using our large 2-acre plots at the Dudley Smith farm, there's so much additional stuff that's happening with field scale studies. We didn't really see that leaching of phosphorus from the cover crop tissues, which is encouraging because we want our cover crops to work. But I think that highlights the benefit of her study was that, she had small scale controlled conditions, and then we also were able to scale that up to big scale field scale. So in terms of the question, lifespan of a bioreactor, rule of thumb is 10 years. The bounds on that are really about 7 years to 12 years before you would replace the wood chips. And so that's another reason why it's a really low maintenance edge of field practice. Rather than thinking about, having to do something in field like a cover crop every year, which of course we always promote for water quality, a bioreactor is, one and done for 10 years. And it's there catching nitrogen that would otherwise go downstream and cleaning that nitrogen out of the water without a lot of input or maintenance required by the farmer. And so we really need all of these tools in our toolbox, our conservation toolbox, to make sure we're having a significant improvement on water quality and tile drainage water quality here in the state of Illinois.
Thank you. Are there any other questions?
Yeah, I've got a question.
Yes.
Laura, has any studies been done on the leaching of like potassium out of harvested wheat straw? Because I've heard, you want to wait until you get a rain after wheat is harvested before you bale it up to let the potassium leach out of the straw into the soil. Has any studies been done on that and how much leaching does happen?
Such an interesting question about potassium. From my experience with the drainage literature, there's nothing that comes to mind in terms of wheat or potassium. In fact, from the drainage studies that I know, there's maybe out of the past 50 years of drainage research, hundreds of drainage water quality studies, there's maybe 2 studies that have any potassium data. And so your question about wheat straw especially is interesting because it's not something I had considered. I will say that part of what we were funded to do at the Dudley Smith farm for our tile plots is analyze our samples for potassium, our water samples for potassium. And so we have been doing that, and it's so unusual. It's created a lot of trial and tribulation in our lab because it's so unusual to analyze drainage water samples for potassium. Again, maybe 2 studies out of hundreds of studies. Hundreds of drainage studies have actually looked at potassium because potassium does not cause any sort of, to my knowledge, environmental health concern and nor human health concern. And so we haven't really looked at potassium loss in tile drainage for that reason. But we have been funded to analyze some of our samples for potassium, and it's been a real mess for us. What I will say is that I suspect our potassium in our tile drainage is mostly driven by, it's generally very low, but our plots that are higher in soil test potassium tend to have a little bit higher potassium in the water. And when we have a large rainfall event and a lot of drainage, like a big drainage event, that's when we see peaks of potassium in the drainage water. But it's our data are just really patchy. And so it's ironic that you're asking about potassium, because it's been a heartburn issue in our lab recently. I didn't really answer your question because I don't have an answer, but does that
Okay.
provide some insight?
All right, thank you.
Okay, thanks.
All right, thank you. Are there any other questions for our presenters? Can we get Andrew, can we get you to share your slides?
Yeah, no problem. Let's see.
So our next presenter is Andrew Margineau, and he is a University of Illinois Crop Sciences Assistant Professor.
Awesome. Thank you for the introduction. So it's good to be here. This is my first time attending a outreach event like this, and I'm glad that I was given the chance to share what my lab is doing at the Dudley Smith farm and then at other places in the States, all linked together on the theme of a soil phosphorus credit. So I think since some of you may not know me, or most of you probably, I'm a newcomer to the Midwest. I came from UC Davis, where I did my training, worked on phosphorus in very different kinds of soil systems, still corn, but corn in Africa. They have big issues with phosphorus out there, but they don't have enough of it. So it's nice to be in a very different context and in a place that is really rich with natural wealth of soils. And that's going to be a theme of what I'll be sharing with you, is that we have a lot of natural capital beneath our feet, and that's thanks to the glaciers that shaped this state. And there's evidence that we might be able to make more of that natural capital. So more on my lab is at that link down there. We work on all things on soils, not just phosphorus, despite my obsession with that element. Okay, so first, a big thanks to the Dudley Smith D Synergy Project for funding this work. And then to two postdocs in my group that did a lot of the lab work in the analyses. As you'll see, the analyses to look at how much phosphorus can mineralize from organic matter is not straightforward. It involves radioisotopes, which are radioactive, pretty dangerous. That's why you see Dr. Lee, Oliver is what he goes by, all suited up. That's a Geiger counter that he's putting his hands by. Basically, he and I would have to suit up and take turns checking each other because of the form of phosphorus that we're using. And then Dr. Wade, he's more of a statistician, soil health guy. Together, the three of us had a lot of fun on this project, trying to derive a potential soil P credit for Illinois. So let's talk more about what I mean by soil P credit. So this is analogous to the soil N credit that I'm sure a lot of you have heard about. And there's a lot of parallels, but there's also a reason to think that a soil P credit might be trickier to nail down than an N credit. And from what we can tell, no one has ever tried or attempted to estimate a P credit. So this is fairly novel work, and I'm excited to share that with you. So the gist of our project is, can we get even just a ballpark estimate of how much phosphorus how much P is one banked up in organic matter, then how much could mineralize over the growing season? So how much is stocked up in organic form, how much can be released during the growing season? So two separate questions. And by answering these two questions, we can come up with a ballpark of, for X% organic matter, ideally, you would estimate you've got 5 pounds of P per acre that will become available to the corn or soybean or to the pasture crop. So the idea then is that during the growing season, so as soils warm up around May into June, things get warm, and in biology, in soils, temperature drives processes. This is why we want to add anhydrous once things cool down. It's the same principle. And in the spring, it works to our favor. We're going to mineralize nitrogen, but also phosphorus from organic matter in soil. So if you can see my cursor here, the trick is we want to understand as P begins to decompose and be released into crop available P, what your soil test value basically is reading, how much of that can synchronize to help meet part of the crop demand. So we don't anticipate, like nitrogen, that organic matter alone can provide all of the phosphorus for high yielding crops, but it can definitely chip into that. So let's try to find out how much can it chip in. Now, there's also implications for nutrient use efficiency, thus the cost of inputs, and also for potential losses. And to me, losses matter first and foremost from the perspective of nutrient capital. So I began with, we are blessed with the wealth of the glaciers in this state. We have the best soils in the world, and we risk potentially losing some of the banked up phosphorus that's naturally there if we don't synchronize when the pea is being given off with when the crop is growing. Now that's down the road. The very first step is just trying to understand how much can this happen. So there's great theoretical reason to anticipate a pea credit. As always, the question is, well, how much? Because things can happen. Follow-up question is, does it really matter? So let's talk a little bit more then about the theory. So why do we anticipate this even being a thing? Why is this worth funding? Let's talk about organic matter in soils, SOM. You probably know that it's largely organic carbon. So organic here just meaning that it's carbon bound to carbon. Different use of organic from USDA certified organic, for example. So organic matter is roughly 56% carbon by mass, just like you and me, dry matter basis. And then it's about roughly 1/10 as much nitrogen as carbon. And then about one more 1/10, so 100th of the carbon equivalent in mass is going to be phosphorus. So again, the N and the P are crop unavailable because they're not the inorganic forms like ammonium or nitrate or orthophosphate. They're bound up to carbon. So microbes in crops, they produce enzymes like what you have in your stomach. These enzymes will cut the bond to carbon and free it up, and then the crop can take it up. So broadly speaking, at global level, biogeochemists, people who study, how dirt and how air works, is how I think of it. They have a fancy word called stoichiometry. So stoichiometry just means the ratios of things. Like the ratio of chips and salsa is never perfect. You always run out of one before the other. You have to go back and get more of the other. Similar thing when it comes to nutrients in soils, when it comes to microbes, that there's never quite enough in terms of the right proportion. And this explains a lot of the things that we see with, say, cover crops, where we will immobilize nitrogen by adding too much carbon, which those microbes go back to get more chips, and then that ties up that nitrogen. So similar concepts that you probably have heard about. For C to N to P, so there's a 3-part stoichiometry here. Roughly speaking, these are the ratios. Now the trick is that when it comes to nitrogen, the 100 to 10, which is a 10 to 1, C to N, that's pretty well constrained. So whether you're in the Amazon or in Africa or in the Midwest, that's going to be pretty constant. And as a result, people have capitalized on this to try to come up with rough ballparks of an N credit, meaning that because we know if carbon is 3%, then we're going to have 1/10 of that as organic nitrogen, and then we can make some ballpark estimates on how much N can be credited during the growing season. So for example, there's plenty of documents out there that give you ballparks. The conservative rule of thumb is that for every 1% organic matter, there's about 20 pounds of N per acre that will mineralize. So this example from Nebraska puts it a little bit higher at 28 pounds per 1% organic matter. Now, there's obvious caveats here, right? So it depends on the weather. This is a potential. In an average year, and there's no such thing, that's how much could be given off from organic matter as a natural process. So Dr. Christensen's work on the unfertilized plots, how much N comes out of the tie line, that's the same situation here. That's a natural process that operates in our systems, whether or not we're doing agriculture. So there's other caveats, mostly soil type, things like texture, how much clay content there is. But already here we see 3 principles that we tested for the P credit: organic matter content, temperature, and soil type, broadly defined by texture and organic matter. Now, if you look very closely at the document from Nebraska, they tuck away here this mention that as you decompose organic matter, you're going to give off other components, not just the N, but also the P. And that's what the H2PO4, that's orthophosphate. That's what your soil test reads as pounds per acre of available to the crop. So phosphorus is trickier. Phosphorus is trickier because we don't ever really bind the carbon to the phosphorus directly. So at the bond chemical level, if you go back to high school chem class, C and N are always bound, but C and P are parted by oxygen. There's always this indirect binding. As a result, we can't always predict what P is going to do. In contrast to N and C are best friends. They tend to track each other. So this is why there is an open question to this day of, well, there's probably a basis for the P credit, meaning as we decompose organic matter, P is going to be given off, but it's going to be a lot more variable is what we anticipate. Now, we've done some work in really high organic matter soils up by Monmouth at the long-term sites, and we found that just in the top 6 inches, there was over 1,000 pounds of phosphorus in this organic form, meaning phosphorus that is stocked up in your organic matter. And that's a fair amount, but there's a lot of crop or a lot of bushels worth of P export in that organic matter. Now, I'm not saying we wouldn't fertilize. I'm just saying, because obviously what we export, we have to put back in at some point. It's simply thinking about, well, if there's a slow release pool already in my soil, can I tap into that and then perhaps refine what I'm applying? Okay, so now the motivation for this work came about from reading this little book here published in 1908. I'm kind of a history buff and I like reading through old agronomic textbooks and just bulletins. There's a lot of knowledge that people 110 years ago figured out and with fewer tools. I think they were honestly better scientists than us today. We've got all these fancy toys and we're still trying to answer the same questions. So this is a book written by the first major soil scientist at the U of I, Dr. Hopkins. And it's called The Farm That Won't Wear Out. So he was a professor of soil science on campus here, though he was based down south and he would commute up to campus. And so a lot of his work has gems like this that make me go crazy because these are fascinating data that he collected 110 years ago. And this page really made me stop. If you look closely, I've underlined and pulled out in red that in 1908, already people were thinking about the fact that across our state, as you go from the glaciated central and north to the unglaciated south, and the Dudley Smith is at that transition zone, that there are inherent differences in how much phosphorus we have banked up. And as you can see here, Hopkins was estimating roughly 1,100 pounds, almost 1,200 pounds, which matches with our data. 100 years later, we came up with almost the same number. There's roughly 1,200 pounds of P in the top 6 inches. And if you go down south, these soils are more weathered, they're older. And so there's a little bit less phosphorus, about 800 pounds in the top 6 inches. So this question of how much P is already stocked up, the total bank account, and what's the withdrawal that's going to happen naturally driven by biology? This has been a question for 110 years. So what we're doing is not new in concept, but we do have fancier tools. And we have a really fancy tool that came about 5 years ago using radioisotopic phosphorus dilution. It's a mouthful. Basically, we can try to estimate how rapidly P is decomposing from organic matter. So that then is the gist of this proposal. What we did to tackle the question was that we wanted to furnish a gradient of the conditions that we thought would impact the P credit. So think again back to the N credit, things like temperature, soil type, and organic matter content. And that last one we know can be influenced by practices like no-tillage or cover cropping. So we use these 3 different sites across the state to furnish a gradient of soil types, of temperature. We had a pretty big emphasis on the soils from the Dudley Smith farm, but to contextualize those results, we chose one up north in the northwest at Monmouth, and then down by Ewing, which is solidly in the unglaciated south region. So just to give you a sense of the approach, it takes someone full-time working full-time weeks, working with radioisotopes to infer a P credit. This is why we're the first, to our knowledge, in the US doing this work. A couple in the EU have tried it out for their systems. So what we did is that in April, we sampled soils. Shown here are those sites that Dr. Christensen works at. And then we Also, at the same time, we're developing the method. So again, for US systems, there's no methodology for this. So we had to make the tool in the first place. As you can see here, there's a little sticker of radioactivity, and that's the key part of this method. And that will be explained in just a second. So to test the effect of soil temperature, we did this at 3 different temperatures in Celsius. So here they are in freedom units in Fahrenheit. From this, we then got a calculation of how much P could potentially mineralize. So note my word choice, potentially. And note that we're also in the lab. This is a simple explanation. These are radioactive substances. We can't release them in the field, or at least the Christensen lab students probably wouldn't want that, or the producers themselves. So it has to be ex situ, out of the field for now. Currently, where we're sitting at is right here. So we've done the first phase on targets, and we're about to enter in the modeling phase on the statistics, where we can try to balance the multiple drivers of the P credit: temperature, soil type, past practices. So what I want to share with you today is the results preliminary on, is there a P credit? And if so, what is it sensitive to? Is it about your soil type most of all, which is a simple answer? Does it track with organic matter content like nitrogen does? So the N credit we know is more or less about organic matter. Is the P credit that simple? It would be nice if it were, but maybe it's not. So the technique itself uses radioactive phosphorus. We use a form of phosphorus called 33P. All the phosphorus that's in your body right now is teeth and bones, is the 31 version. 33 is unstable, it falls apart, it gives off energy that's high, well, it's high in energy, and that's the radioactivity that I keep talking about. The way that this works is that we look at how quickly, if we introduce a spike of the hot, the labeled 33P, how quickly the natural process of organic P mineralizing into the normal 31P dilutes out the 33P. So think of it this way: the higher the P credit, the more rapidly we go from organic P to the unlabeled 31P. And as a result of our total extractable phosphorus, the proportion of the labeled one that we can measure, because it's really hot with energy, that should dilute more quickly. So you're about to see data. The units are rates. This is the rate that it's getting at, is over each day, what is the milligram per kilo, so times 2 is pounds per acre, at which P can be released from organic matter. That is the basis of the P credit, like it is for the N credit. So, and here's why we have postdocs. All right, so I want to contextualize these sites that we use to look at the P credit for Illinois. And on the left-hand side, there's the map of our 3 sites. And on the right-hand side, we've got a table. I blotted out the properties that for now don't interest us, but we'll get to them in just a second. So we've got really here 2 things of interest. We've got total phosphorus, that's the bank account. Then we've got organic phosphorus, and that's typically, in most systems, more than half of the total. So when Hopkins did this work in 1908, he was just looking at total phosphorus. He didn't know how much of it was organic. Again, we care about the organic pool because that is what can be mineralized during the growing season. And if you look closely, there's a few things to kind of think about. One is that we see, just like Hopkins said, there's more total phosphorus in general in the central north part of the state than in the southern third that was unglaciated. Kind of checks out. We've got 200s to 500s for Ewing, Dudley Smith coming in at the highest, actually, and then up by Monmouth, a little bit lower than at the Dudley Smith site. Now, for organic P, we have high numbers. I think the simplest way to think of this is to look at the percent of total, missing a T there, sorry. So if you look at this last column, this is saying that of your total bank account of phosphorus stocked up naturally, in some cases, or at lowest, it's about 59%. And in some systems up like in Monmouth, it's 74 minimum % of your total bank account. That's quite a bit. And down by Ewing, most of your phosphorus, 80% plus, is as organic, which again emphasizes that we should probably look at how much of that can be crop available during the growing season. Okay, so this is, I've cut out from my favorite book in 1908, Hopkins' original estimates of total phosphorus in the top 6 inches, so it's the same depth as this. And we find that if you convert his pounds per acre to ppm, so the milligram per kilogram, it compares pretty darn well with our values. It might be a little bit higher because of legacy phosphorus being stocked up, but overall, it's amazing to me that 110 years ago, they pretty much got it right. So for reference here, we have organic carbon, SOC, C to N. We can see how relatively invariant C to N is. It's relatively constrained. It's not, say, C to N of 4 and then 50. In contrast, we have total P that's a lot more variable than C to N ratio. Also note that how much organic phosphorus you have doesn't always track with how much organic carbon. So again, we're finding evidence for the theory that C and P is a lot more variable than C and N. Okay, so we then answered 3 questions on what are the drivers of the P credit. So we're measuring how much phosphorus could mineralize under optimal conditions. That's the very first step. So this is all lab-based. That's a huge caveat. But I think it's instructive to, as a first step, deriving a P credit. So I'm going to focus on the data from Dudley Smith for obvious reasons. The first finding that we have is that the P that can mineralize from organic phosphorus can be significant. So the way to read this is that we've got the days of the incubation where we let soil be wet and warm and see how much phosphorus can decompose from organic matter. And we go out for 28 days, but you see how there's really a big burst in the first 3 to 4 days. This is just like nitrogen. Most of it decomposes in incubations in the first few days. And on the y-axis, we have the rate. So again, these are rates. And it's milligrams of phosphorus per kilo of soil per day. So you multiply by 2 to get pound per acre. So you're thinking, Andrew, this is 40 pound per acre in one day. You're talking nonsense. That's how much we put on perhaps for 1 year on really high application rate. And you're totally right. But like nitrogen, what we do is that we integrate the area beneath the curve. The bigger point here is that there are pretty appreciable magnitudes. And if you check out the different lines, these correspond to different treatments at the Dudley Smith. So we know here that there can be massive differences induced by only a couple years of treatments. So it is sensitive to how we manage soils. So a couple observations here is that the P-min rate was highest when we didn't add any nitrogen. So Dr. Christensen talked about their plots with 0 N added. Those same plots also had the most P that was mineralizing. What I think is happening is that those systems are starved for nitrogen. So microbes, when they chase after nitrogen from the carbon, they're, as collateral damage, going to mineralize inevitably some of the phosphorus that's also bound up in organic matter. So I think that makes sense. That the cover crop would increase the amount of P-min that can be given off also makes sense. Ariana just talked about how cover crops contain phosphorus in their tissues. So when that gets tilled back in and we sampled in May after kill, that's consistent. We're adding a dose of fresh organic matter which contains phosphorus. The third observation here is that the conventional corn soybean treatments in pasture were overall similar in how much P-min they had. So how much P could mineralize was about the same and overall pretty low. So we're looking at the blue and the yellow line. The pasture frankly surprised me. I would have thought that these permanent systems that have roots growing year round would have the highest amount of P credit. So not sure why. This is interesting. So again, going back to the magnitudes, these magnitudes don't really make sense, but remember, these are rates in the incubation in the lab. So there's some math that we're going to do next to see over a growing season, what is a realistic estimate? In this sense, we're no different from the N credit. You find similar data that on face value doesn't make sense. You have to then model it. Okay, so that's the first point, is that it is appreciable, especially at the Dudley Smith site. Second point, again with the same site, is that this process is highly temperature sensitive, which is not surprising because it's mediated by biology. Microbes and their enzymes are the ones doing the work of decomposing organic matter, and therein the phosphorus becoming orthophosphate. This is just like nitrogen, so it's no different, and that's, I think, a good thing. If P was a different beast when it comes to the P credit compared to the N credit, that would make this even more complicated. So the basic gist of this is that as you get up to 68 Fahrenheit versus 50, there's a marked difference. So in orange and gray, we have pretty cool to cold temperatures. So we've got 50 and 41, orange and gray. And if we have, regardless of treatments, we bump up the temperature to 68 Fahrenheit, we see multiple fold increases. So up to 10-fold more phosphorus that can mineralize. Makes sense, consistent with the end credit. Then, excuse me, the third major theme that we tested, so we talked about soil type and temperature, is whether different practices can influence the magnitude. So for the relative differences for this lab-based first step, can we move the needle based upon from a couple years of cover cropping, like at the Dudley Smith, to, for example, at Ewing from plots that have been under continuous no-till or lime or no lime for about 65 years plus. So we have a range of how long and what has been done. And long story short, if we look at the other sites, because you've seen the Dudley Smith data on the right-hand side, we do find differences. So there's a lot here. Let me walk you through. Basically, on the right-hand side, you've seen this already, just pointing out that the numbers are bigger for Dudley Smith, going up to 28 for the gray treatment. And they're in general a lot higher than the Monmouth and generally higher than the Ewing systems. So this means that at the Dudley Smith, for some reason that we still don't know, those soils have a unique ability to release more phosphorus from organic matter. Why this is, I think, is to be, well, parsed out yet. So if we get into the more specifics, let's start with Monmouth. I know a lot of people think of the soil types, the Sable series up there as the best of the best, but as we just saw at Dudley Smith, we have lower organic carbon, but more P supply power. So this is going back to the opening idea that unlike nitrogen, the P credit may not be as intimately tied to organic matter content. So what we find is that, well, a couple things, just like at Dudley Smith, if you don't add any nitrogen, you have a higher P-min. I think this is, again, the microbes are N-starved, and on their way to access N from organic matter, they inevitably free up phosphorus. Second point is that we have 4 times more phosphorus credit potential when we do no-till, but this doesn't scale with the increase in organic matter. So at this system, which has been 26 years of till versus no-till, there's 17% more organic matter with the no-till than the till, but we have 400% more P credit potential. So this again is showing that the P credit does not simply scale with how much carbon is being built up. Unlike the N credit, it's going to be a little bit different. The bottom panel is showing you Ewing. This is a very different system from Monmouth. These are fragipan soils. On a good day, they got maybe 1.5% carbon, 3% organic matter. These are the unglaciated soils of the south of our state. And here we find that basically, that if you have a unfertilized long-term treatment since 1940, no P has ever been added. There's a lot less P-min than if you've been adding P. So these are really simple contrast comparisons, P or no P. But again, as controlled experiments, they let us take a first step to ballparking the P credit and what can drive it. So I take this to mean that we just have less total phosphorus in the system. And if you recall, the P fertilized treatments at Ewing had about 500 ppm, so about 1,000 pounds of P per acre. And the unfertilized treatments were about 200, so about 400 pounds. So the more P you have banked up in the system, the more can circulate into organic matter and then be released again as the P credit. That's how we're seeing this data. What surprised me is that whether or not you add lime to increase the pH has no real effect on the P credit. And I'm surprised because we know that microbes are pH sensitive if it gets too acidic, and the unlimed treatments are about pH 4.2 versus about 5.5. If it gets too acidic, microbes kind of shut down. And if you bump up the pH with liming, it's good for crops, but also for microbes. So there's no real effect on whether your pH is, in this case, 4 or in the 5s. So what does this all mean? Well, let's go back to the intent of this work, which was, is there a basis? Is there some evidence that a P credit could be a thing? Might it matter? And the short answer is, yeah, I think there is here. There is evidence that P can mineralize from organic phosphorus, and it can be appreciable. And let's talk now about, well, yep, it does matter, or it could matter. How does it matter? And the first thing that we go to is temperature, because that drives biology, and that drives any credit, whether it's N, P, or sulfur, for example. So it is temperature sensitive, and in a very simple way, it tends to track with N dynamics. So that's good news because it's kind of simple. The second question is it sensitive to management, whether it's 2 years or 26 or even 60 years? And what we find is that it's most sensitive to tillage, as well as the application of phosphorus and nitrogen. So under no tillage, it explodes, but it doesn't just track with organic matter. So organic matter does not explain the increase in the P credit potential under no till. That's interesting. Suggests that there's something like biology going on, not just carbon content. If you add more P, there's more P to circulate through this pool. So that's what we found there. And if you don't add any nitrogen, then I think the N-starved microbes are going to inevitably mineralize P when they're chasing after the nitrogen. So we have 2 sites that support that. Second finding is that there's a somewhat sensitive to cover cropping, but the magnitude is relatively minor. So that's interesting. And the third point is that unexpectedly liming doesn't really play a role. So what this says to me is that we should focus on tillage. And I say tillage and not so much P and N, because our treatments, again, were either no N or at normal rates, and same for P. No one is not adding P or N, or very few people. So to me, this means that we might ask within the range of rates that are typically used, then does N or P rate matter for the P credit? But we do see now that no tillage has a pretty big benefit potentially for the P credit magnitude. I think a key takeaway when thinking about the sensitivity of the P credit to how we manage soils is that it's not simply reducible to the content of organic matter and thus organic phosphorus, which means that this is going to be trickier than the N credit. It's going to be tough to have ballparks of 1% organic matter. You can think of 20 pounds per acre of N. Might be a bit more complicated. Now, the good news is that we've identified from this work how it's complicated. So we know what to look for. We know also what not to look into. So liming is off the table, same with cover cropping for now. So the next steps here is that we're going to go out into the real world. I've talked with Len and Jack already. We're a little bit delayed, sorry about that, on doing some on-farm sampling across across this diversity of real world contexts. So now we're going to go back off of these research trial sites and look at real operating farms that have different kinds of practices and histories, trying to parse out under that complexity, what does the P credit look like? So what we hope to get from this in the next 6 months of this project wrapping up is coming up with the first pass P credit. So you've seen the P min data, which is how much P can mineralize from organic matter. Then that has to be processed into a ballpark of how many pounds per acre of P could you potentially credit. Obviously, this is the very first step of a research program. We hope to bring it to the point where we're going onto farms and do some trials to try to corroborate whether our estimates from the lab pan out. The trick is that this is a radioactive technique, but we can get creative with other ways to try to test this in the field. Okay, so I'll leave you with this gorgeous photo of the Dudley Smith farm where we took some of our samples from, and I'd be happy to take any questions.
Are there any questions?
I have a question for the audience.
Yes, go ahead.
Has anyone heard of a P credit before from agronomists or crop advisors, or an N credit for that matter? I know in some states there's more talk of N credit. Since I came here, I haven't really heard much about that compared to, say, Iowa. But I'm just one person, and your combined experience is centuries of experience, honestly. So I'm curious to get the thoughts from the audience on this.
Maybe while they're getting their thoughts together, you have one question. Is there a difference in livestock history on the land at the 3 sites?
It's a good question. So there's no livestock that I know of at Ewing down south. At Monmouth, I think there was some livestock rotation at some of the plots now. But I think for the past 26 years, the soils that you saw from that region didn't have livestock. So it's only the Dudley Smith pasture site that you just saw that would have the livestock. And that had the lowest P credit, being in pasture, which is unexpected. Another question we have here is, how does cover crop affect the P credit? Well, for what we found from the Dudley Smith sites, is that not very much. There's a small positive gain, but in the end, it seems like if you adopt no tillage, that might be the bigger effect on the size of the P credit. This is all preliminary data, but that's what it suggests so far.
Any additional questions or some thoughts onto the question Andrew presented? We will be giving out an evaluation, so maybe they can think about it and provide some feedback for you on the evaluation form.
That'd be great. Great, well, thank you all for your time.
All right, thank you. So we really want to make sure that our outreach events are meeting your needs. So can you please take a moment and complete this brief survey? You can either use your mobile device to scan the QR code, and I can also place the link to this survey in the chat box as well. I'm going to place the link in the chat box. Okay, there's the meeting survey. And we would also like to thank all of our presenters for sharing their research with us today. And we really appreciate all of the participants who joined us today for our Dudley Smith outreach event. If you are a certified crop advisor and you're needing your continuing education units, I also have a QR code for you to scan for the afternoon session.